We've talked about stoichiometry now and how to do a problem where we start with grams of reactant and end up with grams of a product. And now we're going to look at what happens if you don't have enough of one of the ingredients. So we're going to go back to talking about the sandwiches. So 2 slices of bread, 3 slices of meat, 1 slice of cheese gave us 1 sandwich. It's a recipe, a formula, an equation for making sandwiches. If we have 50 slices of bread, 60 slices of meat, and 40 slices of cheese, how many sandwiches can we make? Just real fast off the top of your head. Can you figure that out? Like in 5 seconds? I can't. You kind of have to think about it for a minute. So let's think about it for a minute. You had an answer. What was your answer? 20. 20 is the right answer. So how do we figure that out? Well, basically what we have to do is we have to look at the amount of bread. How many sandwiches could we make with 50 slices of bread? So let's write that out. We can do this problem in our head because the numbers are nice. 50, I'm just going to call it bread. 50 slices of bread. And we're going to get 1 sandwich for every 2 slices of bread. That's what we're doing in our heads. And we say, oh, well, we could make 25 sandwiches. Let's call it sand. Well, what if we have 60 slices of meat? That's enough meat for how many sandwiches? 20. Because there's 1 sandwich. 1 sandwich for 3 pieces of meat. So 20 sandwiches if we use up the bread. And I heard someone say, well, what if we just use 2 pieces of meat? Yes, but you're working at Quiznos, and the rule is, they get this much meat. And if you skimp on the meat, the customers are going to get unhappy, and they're going to complain, and they're going to tell your boss, and you're going to lose your job. So you can't do that. You can't do it. 40 pieces of cheese. Well, that's 1 to 1. We could make 40 sandwiches out of that much cheese, right? So the cheese is enough to make 40 sandwiches. The meat is enough to make 20. The bread is enough to make 25. So think about this. You're going along, you're making sandwiches. You make 10 sandwiches. You make 20 sandwiches. You ran out of meat. You're done, right? It doesn't matter that there's more cheese and bread left. You have to stop. There's more cheese after 20 sandwiches. Yeah, you could make cheese sandwiches, but that's not what the people ordered. Yes?
The examples in chemistry where you say you can't make any more sandwiches, so the reactants make
Something else?
the reactants themselves after one of the elements.
There probably are. There probably are situations where when one of the ingredients runs out, another reaction occurs and another product forms. We don't talk about those in general chemistry. No, we don't make cheese sandwiches in general chemistry. It's a good question, though. And that's, one of the limitations of this analogy. The analogy I used was a bicycle factory. And you need 2 wheels and 1 frame to make a bicycle, right? So, can you make bicycles with just 1 wheel? No, that just doesn't work at all. That's why I like that analogy better. You can make a unicycle, but only if you had a unicycle frame, right? You can't make a unicycle out of a bicycle frame. It's just not going to work. So, this is an important idea because when we translate this into chemicals, people lose their minds. And so we have to remember when you run out of an ingredient, you stop, right? Because people do crazy things. They'll have a question, with chemicals saying, okay, you've got this much of this and this and this, how much product can you make? And they'll do crazy things like they'll add the 25 and the 20 and the 40, and they'll say, we can make 85 sandwiches. No, you can't, right? No, it's not going to work. Because you ran out of one of the ingredients. The ingredient that gets used up is called the limiting reactant because it limits the amount of product. And this sort of a situation when you're cooking is pretty common. It's really rare to have exactly the right amount of each ingredient. Another book I teach out of uses pancakes. So you've got eggs and oil and flour and baking powder. Have you ever made anything where you had exactly the right amount of flour and eggs and everything? No. Usually you actually end up having leftovers of everything. And it's also not uncommon to have one ingredient that you had just enough for. Like you make a cake and you use a box of cake mix. Well, you have to put oil and water and eggs in there. You've got plenty of oil, water, and eggs, and you used up the box of cake mix. So you're done. You can't make any more cakes. Then you have to go to Fresh and Easy for the third time that day because, you forgot that there were 36 children in the class and they need more cupcakes. That's never happened. So in this example, I'm not sure why there's no word in that blank. What's the limiting reactant? Oops, the meat. The meat was the limiting reactant because it limits how many sandwiches we can make. So let's look at chemicals. A stoichiometric mixture is one that contains the exact right amounts of each reactant in order to form product. So that's in the kitchen, you've got exactly what you need for your recipe. Very unusual. We don't usually have this happen in chemistry either. So when it says stoichiometric mixture, it means you have the relative amounts of reactants that match the numbers in the equation. So if you're doing this reaction between nitrogen and hydrogen to make ammonia, it means that for every 1 mole of nitrogen, you have 3 moles of hydrogen. You have just the right amounts of each. So with the sandwiches, the amount of bread and cheese and meat would be multiples of the numbers in the recipe. And so you would come out exactly even on everything. So in this illustration, before the reaction starts, here in this container, for every 1 nitrogen molecule, there are 3 hydrogen molecules. And they've put red dotted lines around that so that you can see them. They've grouped them for you. And so what happens when that reacts is that the things in this red circle react to form 2 ammonia molecules. And this one, that's the right ratio to make 2 ammonia molecules. Okay, does that make sense? You've got just the right amounts of everything. That's a very rare situation. Usually we have a limiting reactant mixture where we have not enough of one of them to react completely. So here, same equation, here's one group in the red lasso, 1 nitrogen, 3 hydrogens. Here's another group and another group, but we can't make any more groups because here we have 2 nitrogen molecules and there's no hydrogen to react with it. You're making sandwiches and you ran out of something and this is what's left over. You've got extra cheese when you're done. So when this reaction occurs, we're going to get these 2 ammonias and these 2 and these 2, and what happens to the nitrogen? It's still there. When we made those sandwiches, what happened to the extra bread and cheese? It's still sitting there on the counter. It doesn't disappear, it's just sitting there. But it's not going to react, it's not going to make itself into sandwiches. So the limiting reactant is the one that runs out first and limits the amount of product. In that illustration, it was the hydrogen. So when we have a situation like that, which is usually how the situation is, because just like in cooking, it's really hard to get exactly the right amounts of everything. To determine which reactant is limiting, we need to determine which reactant is limiting in order to correctly calculate the amount of products. Just like with the sandwiches. We've got all this meat, cheese, and bread. To figure out how many sandwiches we need to make, or can make, we need to find out which one is going to limit, which one's going to run out. So methane and water can react to form hydrogen and carbon monoxide. Is this, this equation's balanced. We've got one carbon, one oxygen, 6 hydrogens, 2 plus 4, 6 hydrogens. So if this is our mixture, here we've got methane and water. Those are going to react to form these products, and these two can react to form those products, and these two can react. But what's left over? We got this guy and this guy. They have no water to react with, so they get left over. What's the limiting reactant? The water. The one that gets used up. In that example, the amount of products that can form is limited by the water, so we say the water is the limiting reactant, and we say that methane is in excess. There's extra methane. And in the questions that we've been doing with just learning stoichiometry, they'll say you have this much of one reactant and an excess of the other. So they've basically been telling you this is the one that's important, the other there's plenty of, we don't need to worry about it. So now we're going to start worrying about it. So for those of you who like lists of steps, here's a list of steps. So when we have a limiting reactant situation, the first thing is we need to write and balance the equation for the reaction. On an exam, I'll do this for you, but in the homework, you may need to do this yourself. If your equation is incorrect, the answer to the whole problem is going to end up being incorrect. So it's really important to make sure that you get the right equation. The next step is to calculate the masses of products that can be formed from each reactant. So just like what we did with the sandwiches, we looked at each reactant separately and calculated how much product. How many sandwiches can we make from the bread? How many from the meat? How many from the cheese? And then step 3, you identify the smallest number of product, or smallest mass of product. That's the amount that you can make. That's your answer to how much product can be made. The limiting reactant is whichever reactant gave you the smallest number. So let's do an example. You react 10 grams of A with 10 grams of B. What mass of product will be produced, given that the molar mass of A is 10 grams per mole, B is 20, and C is 25. They react according to the equation A plus 3B goes to 2C. Now this equation, this problem looks a little funny because there's no real elements here. A is just representing an element or a compound, and B and C are representing elements or compounds. We're giving you their molar masses, and we're doing this with nice roundish numbers so that it takes some of the math out of it. So again, it's a good idea to use that balanced chemical equation to organize the information. 10 grams of A. So under A, I'm going to write 10 grams. Well, I really should put the 0. 10.0 grams. And it says I have 10 grams of B. So I've got 10 grams of B. What mass of product? Well, there's only one product. It's C. So that's our question mark. It says what mass, so we want grams there. And then it gives us the molar masses, so we don't have to calculate those or do anything with that. So our overall pattern here is grams to moles to moles to grams. Because we're given 2 reactants, we need to do 2 calculations. That's one way to recognize a limiting reactant problem. The problems that we've done up until today, they just gave you the mass of one reactant or one product and asked you to find another one. Now they're going to give you two masses, and that means you need to do a separate calculation with each of them. So let's do A first. 10 grams of A, and we're going to have 3 fractions, and we're going to follow our path, grams to moles to moles to grams. So grams of A to moles of A to moles of what? C. Moles of C, because this is what we're trying to figure out. There are other ways to do the problem. I think your book presents another way as an alternate, and if you like that way, go ahead, but I'm not going to teach it because it confuses people. Grams of A to moles of A to moles of C to grams of C. Then we stick our units in so they're going to cancel out. Grams of A cancel out. Moles of A cancel out. Moles of C cancel out. And then we need numbers. Where do we get the numbers for the middle mole to mole term? From the equation. So in front of C, we look in the equation, it's a number 2. So we write 2 in front of C. What's in front of A? Nothing, which would be a 1, right? So 1. The first term is the molar mass. We don't need to calculate it because they gave it to us. The molar mass of A is 10 grams per mole. So 10 goes with gram. So 10.0 grams per 1 mole. And then for C, the molar mass is 25. So 25 goes with gram, and 1 mole goes with C. 1 goes with moles. So then we do the math, and we end up with 50. Ten divided by 10 times 2 times 25. Okay, 1 down, 1 to go. So now we take the other ingredient, the other reactant. There's also 10 grams of that. Yes, question?
Mole of C, is it 2 moles of C or is it 1 mole of C?
In the denominator,
Yes.
it's 1. And that's a good question.
Oh.
The 2 only shows up in the mole-to-mole ratio. So the coefficients from this equation only show up in the mole ratio. They do not show up over here. Okay? Because up here we have 25 grams per 1 mole.
Gotcha.
Molar mass is always per 1 mole. And that's a thing that stays fuzzy for a lot of students for a long time. So we keep asking, and let's get that cleared up. So the other one is grams of B. So it's going to be a very similar calculation. 3 arrows in our grams to moles to moles to grams. So we've got 3 fractions here. Grams of B to moles of B. We're still trying to find the product. When we did the sandwiches, we were calculating number of sandwiches for everything. We weren't taking the bread and calculating the amount of cheese or doing anything funny like that. Moles of B to moles of C to grams of C. And then we put our units in so they cancel out. It's supposed to be a C. We got all the units in, and then we look for numbers. The middle term, moles to moles, this comes from the equation. In front of B is the number 3. And in front of C is the number 2. We used the coefficients, we're done. We're not going to use those again. You only use them once. The last term ends up being exactly the same. So there's a little bonus there, because you're calculating the mass of product and the molar mass of the product is not changing. So that last term will be exactly the same. The first term, molar mass of B, they gave it to us up here, 20 grams per mole. So 1 mole of B weighs 20 grams. I should be able to do this in my head, but life is too complicated right now to think about things like that. 8.33. Is that what you guys came up with? Anybody? Thanks. 8.33 grams of C. Now just looking at the equation and the masses, it's not at all obvious that one of those 10-gram amounts is going to make so much more than the other, right? And that's why you actually have to do the calculation. So if we use up all 10 grams of A, we can make 50 grams of C. If we use up all 10 grams of B, we can make 8.33 grams of C. So what amount can we actually make? The 8.33. So at this point, you've done all the hard work, and all you do is you look at those two numbers and say which one is smaller. Question?
Yeah, I just didn't get why we did two equations.
Why did we do two equations? That's a good question. Because we're given two amounts of reactant. So it says 10 grams of A and 10 grams of B. In all the problems we've done up until now, they just said like 10 grams of A, and they asked for product. And then you do one calculation. When they give you two masses, you do two calculations. If it's a more complicated reaction and they gave you three, you'd have to do three equations. Okay, that's a good question. So we just look at the answers we came up with and see which is smaller. Don't add them together or do anything crazy. Just put a box around the smaller one. This is the amount of product. Question?
Will there be an instance where we have to work backwards? They were given C and we want to determine what the limiting reactant is?
We don't usually work limiting reactant problems backwards. There will be more straightforward stoichiometric problems where we give you a mass of product and say how much reactant would you need to make this. That definitely will happen. But the limiting reactant problems in this class, we will not work backwards. What mass of product? I was just realizing, did they ask a question? Yeah, they did ask a question. Sorry. So this is our mass of product here. Now sometimes they also ask another question. Which reactant is the limiting reactant? To figure that out, you put your finger on the smaller amount of product and you trace back to the beginning, and that's the guy right there. Whichever one gave you the smallest number. So in this example, B is the limiting reactant. That's what gets used up. As you're going along making C, you make 4 grams of C and 8 grams of C, and when you get to 8.33 grams of C made, you run out of B and the reaction stops. And you've got a bunch of reactant A that's just sitting there, just like the cheese on the counter, just sits there. So we can't simply add the total moles of all the reactants and decide which reactant mixture is making the most product. You actually have to do these calculations, okay? There's no shortcut. Question?
Must be the limiting reactant because of how much it was on the sample. It's only 10 grams and it's 20 grams per mole. But the equation says we need 3 of B. Is that why it's the limiting?
So the question is, why is B the limiting reactant? Does it have something to do with, oops, I didn't mean to write on that, with it being 20 here and 3 here? Those definitely do play a factor in it.
But also, it's only 10 grams of B versus 10 grams of
Yeah, there are kind of mental games you can play looking at the ratios and stuff, which with nice numbers like this, you can kind of do that. And you say, oh, well, 10 grams of A, that would be 1 mole. And if B weighs 20 grams and I need 3 moles, then I'd need 60 grams of that. And you can do that with a simple thing like this. And it's good to think about that, but that's not a good long-term strategy. No, it's not a good strategy because everything else is going to be more complicated. This really is the most straightforward, simplest way to find the answer.
It's a little bit like the maximum common multiple and minimum common divisor.
It is a little bit like that, yeah. Well, let's do another one. How many grams of ammonia can be produced from the mixture of 3 grams each of nitrogen and hydrogen by the Haber process? What's the Haber process? This is the Haber process. Extra information thrown at you. How many grams of ammonia? That's the question. Question mark, grams. A mixture of 3 grams each. So we've got 3 grams of nitrogen and we've got 3 grams of hydrogen. And the question is, how much ammonia can we make? So we look at this and we see they gave us 2 masses, 1 of each reactant. We need to do 2 equations. 1 for the nitrogen, 1 for the hydrogen. And our path is still grams to moles to moles to grams. So it doesn't matter which one you do first, but I usually do the first one first. Why not? 3 grams of nitrogen, and we're going to have 3 fractions. Grams to moles to moles to grams. Grams of nitrogen to moles of nitrogen. To moles of what we're trying to find, to grams of what we're finding. We're going to divide by grams of nitrogen, so those units cancel out. Divide by moles of nitrogen, so the units cancel out. Divide by moles of ammonia, so the units cancel out. I hate it. I know it did. There's these little buttons that I don't know why they're there. Just to get me. That's why they're there. It's a conspiracy. Yes?
Since nitrogen and hydrogen are diatomic elements, would we have to do N2 rather than just the molar mass of N2, or just N?
That's a good question. These are diatomic elements. What we're going to do is we're just going to use the formula. And so when we calculate the molar mass of nitrogen, we do use that too. And so it's not 14, it's 28 grams. But we're not going to throw that number 2 into other places. So 1 mole of nitrogen has molecules, and each molecule is 2 nitrogen atoms. Good question. Let's do the middle one first. How many moles of ammonia? 2, right? This is from the equation. 2 moles of ammonia to how many moles of nitrogen? 1. 2 to 1. So now, the first one with the nitrogen, actually I need space over there. I'm gonna do my molar masses up here. So for nitrogen, N2, 2 times the mass of nitrogen. So 28.01. 1 mole of nitrogen weighs 28.01 grams. And then for the last one, we need the molar mass of ammonia, which is 1 nitrogen and 3 hydrogens. which is 17.034. And again, that's with the grams. Molar mass, mass of 1 mole. Okay, that's what molar mass means. Now we get out our calculators. 3 times 1 divided by 28.01 times 2 divided by 1 times 17.034 divided by 1 equals. Our initial number of 3.00 had 3 significant figures, and so I'm going to write this, which is a potential final answer with 3 significant figures. The calculator is saying 3.6488397. I'm going to round that to 3.65. If we use up all the nitrogen, we can make 3.65 grams of ammonia. So that's 1 down. Now we need to calculate with the other reactant. 3.00 grams of H2. And so this is going to follow exactly the same pattern. Grams to moles to moles to grams. Grams of hydrogen to moles of hydrogen to moles of ammonia. We're starting in different places, but we're ending up at the same product. Grams of ammonia. And then we put units in the denominators to cancel these guys out. We get all our units in place. Middle term comes from the equation. NH3, we look up here, is a 2. Put a 2 in front of there. For H2, it's a 3. So we had a 3 down here. The molar mass of the last one is the same because it's the same compound. So we don't have to calculate that again. The molar mass of hydrogen is 2 times 1.008, which is 2.016. 3 divided by 2.016 times 2 divided by 3 times 17.034. $16.9 grams of ammonia. And like I mentioned earlier, there are other ways to solve a problem like this. But in my years of teaching, I have found that for beginning students, this is the most straightforward way. We've got a pattern, and we can just follow the pattern, pick the answer, and be done. The other ways involve a little more thinking and understanding. If you're good at thinking like that, they might be a little bit shorter, but it involves too much thinking for most students. And when you're putting this into your calculator, go straight from left to right, top to bottom. So 3 times the top, divide by the bottom, times the top, divide by the bottom. Go straight across like that, and then you won't have any problems. So we got two numbers here. What's our answer? It's the smallest one. Just choose the smallest one.
It's just asking for grams.
It's asking how many grams of ammonia can be produced. And so this is our answer, 3.65 grams of ammonia. The limiting reaction will be the nitrogen, because as the reaction goes along and we use nitrogen and hydrogen to make ammonia, when we get to 3.65 grams of ammonia made, the reaction stops. There's enough hydrogen to continue on to make a total of 16.9. But just like with the sandwiches, we ran out of meat. We can't make the right sandwich for the customer if we don't have meat, and so we stop.
Is the question asking which one is the limiting reactant?
It is not specifically asking that, no. So some questions, it will ask which is the limiting reactant. And then you need to identify that. And that'll happen on your pre- and post-lab questions in lab. It'll give you something like this, and it'll say what mass of product can be made and what is the limiting reactant. And so sometimes what students do is they write all this out, and then they stop. You're going to lose points because you're not actually answering the question. You need to specify this. This is the amount of product, and just a box or a circle around it is good enough for me. They chose this. If it asks you for limiting reactant, you can circle that and write LR for limiting reactant. But you have to specify. It's a real shame to understand how to do the whole problem and then lose points just because you didn't follow through and identify what your answer is.